Hi, my name is Shen, and I just graduated from Penn last year, where I did my undergrad in systems and my master's in data science. Today, I'll be telling you about my DATS practicum project on predicting academic success of master's students using application data. I was advised by Dr. Boonthao Liu and Ira Winston. While the admissions staff has lots of experience and intuition with identifying good students, every year there's always a handful that are not able to graduate. This is frustrating for both the students and the administration. So we want to create a more accurate way to identify the right students from their applications. We have only recently accumulated enough application data to analyze. So this project aims to create a data-driven approach to help admissions identify which students will struggle to graduate and which will succeed at Penn. We also aim to find which specific factors in the application profile are most indicative of future academic performance. Now, the dataset has application information of students who enrolled in the Penn Engineering Master's program through the regular admissions process. This includes their past education data like their school, major, GPA, degree received, etc., standardized test scores such as the GRE, English tests like the TOEFL and IELTS, and other demographic information like gender and international status. There are over 10,000 applicant institution records, so to elaborate, a student with multiple past degrees would have a separate entry for each degree. And then there are over 5,000 graduation results, which is basically the GPA that they got when graduating. And on the left, we see the distribution of students across enrollment years spanning from 2000 to 2018. And then below that, we see the GPA distribution with most around 3 to 4, and then a spike at 0. As we see in the real world, data is dirty and often incomplete. So a big chunk of my work was compiling a usable data set and developing an approach that would give us useful insights in spite of this imperfect data. So the first challenge I encountered was unexpected missing data. There's an uneven distribution of student enrollments from year to year, missing IDs and other fields. So seeing this, we investigated the data source and discovered that the admission system went through several changes over the past decade, and the information was not all properly transferred. Understanding the root of the issue, we were then able to retrieve the missing data and then compile a much more useful data set. And then the second challenge I had to deal with was incomparable data. So some fields were user input, so we had to standardize spellings, abbreviations, typos of names. Also, a big issue was that schools use different grading scales. Some have GPAs out of 4, some out of 5, some percents, honors, letter grades. So I had to create a normalized system where everything would be on the same 0 to 1 scale to allow me to compare them directly. And then the third challenge was just missing information altogether. So the admissions data doesn't contain school rankings, which we would believe is an important signal of a student's preparedness. So to deal with this, I augmented a selectivity feature based on a compilation of ranking lists like the QS World Rankings and US News Report. Also, are missing English test scores because native speakers don't have to take a test. And for students who do need to take the English test, some provide TOEFL while others provide IELTS. So I created a separate English ability feature where I group people based on the ranges of their test scores, and then native speakers are grouped with the top scoring students. And then finally, some like GRE test scores were missing from the main data set. So the main data set had only one test score per student, while there's a supplemental data set that has all of the students' submitted scores. There's no documentation on how these scores were selected, so I had to reverse engineer the process to figure out if they were being super scored by section or by total score. And to address the goals of identifying top and bottom performing students and which factors are most important, I decided to use a machine learning approach. First, I start with a classification problem to develop a model that can predict if an applicant can graduate or not. And then we add different GPA thresholds and create models that predict whether the student will hit a GPA above or below benchmarks like 3.0, 3.3, etc. And then I evaluate the models by test set accuracy and F1 score. I also create regression models to predict the actual GPA and use multiple types of evaluation criteria on the predicted GPA and percentile rank. So percentile rank gives us an idea of how well the model can distinguish between relatively stronger and relatively weaker candidates. We evaluate these numbers based on mean and median absolute percent error. And for each student, I place them in both predicted and actual GPAs and percentile ranks in buckets based on what range they lied in. For instance, there's a low bucket, medium bucket, and a high bucket. So I look at the percent of records that were correctly put in the same bucket as the actual records. And before running the actual models, we have to address the inherent class imbalance issue of the data set. Most students end up graduating. So I resolve this in two different ways. One, by using models that reweight the training data to get class balance. And two, by upsampling the training data to get a positive negative class 50-50 ratio. So I try several different models, including logistic regression, SVM, decision trees, k-nearest neighbors, and linear regression. But in both classification and regression, we select the random forest as our best model for its relative accuracy and its features importances vector, which show us which features were the most important to that model. And then we can infer that these are the most influential in predicting graduation and other GPA benchmarks. So for predicting graduation, we see the features with the highest importances are average Penn GPA of students from the same prior institution, GRE writing percentile, ratio of students' GPA at the prior institution to the average GPA from that institution, and then the student's GPA at their prior institution. Most surprising is the fact that the prior institution selectivity has relatively low importance, which goes against commonly held intuition. We see all these trends generally hold for other GPA thresholds and in the regression model. And as we increase the GPA benchmark, the ratio of the student's GPA at the prior institution to the average GPA from that institution becomes more important. These findings suggest to us that GPA is very important, and when choosing between a candidate with a higher GPA at a lesser known school versus a candidate with a lower GPA from a prestigious school, we should pick the student with the higher GPA. Now, we also note that the accuracy in the regression task for both bucketing schemes is around 50 to 55%. So the most we can conclude from the regression endeavor is that while the set of features may work to predict our classification tasks, it's not sufficient to accurately predict exact student GPAs. So there's a couple main limitations to this study. First, we can't distinguish between students who couldn't graduate because of extenuating circumstances, like medical reasons, family leave, etc., versus a lack of academic preparedness. We found that GPA is a helpful metric, but it doesn't reflect the full picture of a student in terms of curriculum difficulty and course load. Harder classes and heavier workload may result in a lower GPA, but the student may be more prepared academically. And then school ranking data was very, very limited and had to be manually compiled from several different sources. And there's no universal ranking system that has both international schools and small liberal arts colleges and community colleges. Now, based on our key findings, I recommended that we prioritize applicant GPA over school ranking, and applications should use as many predefined options as possible to minimize any user free-form input to make the data cleaning much easier and matching records a lot easier. And then the initial data set we had actually included letters of recommendation, but it was very, very minimal. None were archived before the year of 2015. So admissions should make sure that these letters of rec are saved and that the ratings of these letters of recs are also archived. Now, also should continue obtaining more institution data like the rankings and average GPAs from these different institutions, since the average that I had to use was among the enrolled Penn students, not of all people who applied. And then one final thing I'd recommend would be to build a tool based on these feature importance weights that the models identified so that it can actually make admissions jobs a lot easier as like a supplemental tool. So thank you for tuning into my presentation. I hope you find that my learnings were helpful on your data science journey.